Okay, in this video we'll be going through the 2013 Level 3 Mechanics Exam. So the way I recommend you watch this video is to pause at the start of each question, try the question yourself, and then check with me to see if you got the answer correct. Okay, so moving on to question 1, show that the angular speed of the ball when released is 17 radians per second. Okay, so our angular velocity we know is 2 pi over t. And if you're unsure why our angular velocity is 2 pi over t, if we think about our linear velocity, where its velocity is distance over time, we can imagine that if we are going in a circle, the distance of that circle in radians is 2 pi, so that is our 2 pi part right there. And our time to go around the circle is 1 period, which is our t. So we also know that frequency is equal to 1 over t, and therefore our angular velocity can be rewritten as 2 pi f. Now we can see in our diagram that our angular frequency is equal to 2.7, and so we can plug that in. And that gives us an angular velocity of 16.95, which is roughly equal to 17 radians per second. Show that the average angular acceleration of the ball before it is released is 67.9 radians per second. Okay, for this question we can use the equation that our angular frequency finally is equal to our angular frequency initially plus our angular acceleration times our time. Now initially our angular frequency is equal to 0, so we can kind of cancel that term out. And what we're left with is our angular frequency finally is equal to the angular acceleration times the time. Now we can divide both sides by our time, and we get angular frequency over time is equal to our angular acceleration. Now in the previous question we found our angular frequency, and our time is given here as a period of 0.25 seconds. And therefore our angular acceleration is equal to 16.96 all over our time, which is 0.25, and that gives us an angular acceleration of 67.9 radians per second, which, as you can see, is the value that we're trying to find. Calculate the rotational inertia of the ball. So we know that our rotational inertia is equal to our torque all over our angular acceleration. This is just a rearranged form of our t is equal to I alpha. Now in the previous question we found our angular acceleration, however we do not know our torque. So we can find that. We know our torque is equal to force times distance. And remember, our distance is the distance from where the force acts to the object's center of mass. So if we go back up to our diagram, we can see that a tangential force of 0.48 newtons is applied, and the radius of the ball is 0.034 meters. And so what that means is that if we have a ball, a force is going to be applied right here of 0.48 newtons, and the distance from its center of mass, which is the radius of the ball, because the balls are uniform, is 0.034 meters. And so this distance right here is the distance that we're going to use in our equation, and this force is the force that we are going to use in our equation. And so therefore, our torque is equal to 0.48 times 0.034. And this gives us a torque of 0.01632 Newton meters. There we go. So now we can plug our values into our equation, where I is equal to 0.01632 all over 67.9, which is our angular acceleration, which we found in the previous question. And this gives us a rotational inertia of 2.4 times 10 to the negative 4 kg meters squared. There we go. Okay, so for this first situation, the ball is not rotating, but is given the same linear speed. Okay, so if it's given the same linear speed, that means its linear EK is going to be the same, right? Because our EK is equal to half mv squared. So the ball's mass hasn't changed because the ball itself hasn't changed, and if the ball's linear speed also hasn't changed, then it will have the same EK. Now, due to conservation of energy, we know that EK is equal to EP in this situation. So the EK when it's released is going to be equal to the gravitational potential energy at the top of its height. And so it would have the same EP, and we know our EP is equal to mgh. Again, the mass of the ball remains the same because the ball itself hasn't changed. G certainly has not changed because, it's G, right? G doesn't change. And so the height of the ball has to be the same. It has to reach the same height. And so in scenario I, the height of the ball does not change. Just a quick side note, you would have to write more than what I've written in order to get marks. Write what I just explained and you will get the marks. But you can't just write the height of the ball does not change. You have to explain your reasoning. I just explained it in words because I can't be bothered writing it. So, sweet. Okay, so in the second scenario, the ball is solid instead of hollow. It has the same mass and the same radius with the same amount of total work done to the ball. And it also has the same angular speed. Okay, so because the ball is now solid, so if we have a solid ball compared to a hollow ball, like so, a greater proportion of its mass of this solid ball is closer to the axis of rotation. And because I is equal to mr squared, where m in this case is the mass of the ball, and r is the effective radius. And so what I mean by effective radius is that if we have a perfectly hollow ball, so a perfectly hollow ball means all its mass is on the outside ring. And so the effective radius, let's say, is 0.5 meters. However, if we have a solid ball, its effective radius in terms of rotational inertia is going to be smaller because majority of its mass is closer to the axis of rotation. So even though it has the same 0.5 meters radius, its effective radius is smaller. And so in this case, the effective radius is smaller, and so it has less rotational inertia. And so therefore, if both balls are given the same angular speed, less work needs to get done to rotate the solid ball in comparison to the hollow ball. And so therefore, if less work is being put into rotating the solid ball, more work can be put into its linear speed compared to the hollow ball. And so if more work can be put into its linear speed, it would have a greater linear kinetic energy and therefore a greater gravitational potential energy, and therefore it can reach a higher height. And so the solid ball is going to reach a higher height than the hollow ball. And so therefore we can say that the solid ball will reach a higher height compared to the hollow ball. There we go. Okay, question 2. Calculate the size of the centripetal force acting on the ball at the instant shown in the diagram. So we know that our Fc is equal to mv squared over r. Now we're given the mass of the ball as 0.25 kgs. We also know that the velocity of the ball is 4 meters per second up here, and the radius is given as 1.2 meters. And so we can just simply plug in those numbers. 0.25 for the mass of the ball, times its velocity squared, which is 4 squared, all over the radius, which is 1.2, and this gives us a centripetal force of 3.33 newtons. There we go. Explain why the ball moves the fastest at the bottom of the circle. Now if we look at our circle, when the ball is at the top, this is where it's going to have the most EP, right? Because EP is mgh, if the h is at its highest point, which it is at the top of the circle, this means that EP is going to be the highest at this stage. Now because energy is conserved, that means EP is equal to EK. At the lowest point, where it's going to have the least amount of EP, it's going to have the most amount of EK. Now we know that EK is equal to half mv squared, and so therefore the only changing factor in this equation is the velocity, because the mass of the ball does not change between when it's at its highest point and it's at its lowest point. So the only thing that can change is its velocity. So when it's at the lowest point, it has the most velocity because it has the most amount of EK. So we can write that energy is conserved, and therefore as the ball moves down, the EP is being converted into EK. Therefore, at the bottom, the ball has the least EP and therefore the most EK. Thus, as EK is equal to half mv squared, as mass of ball does not change, the ball must move fastest at the bottom. Alright, that's a very rough answer. The concept itself will get you full marks. For this question, it is a merit. But don't write bullet points like I have. Like, you have to write it in full sentences. Alright, sweet. Okay, so diagram 1 shows the gravitational force acting on the ball at the top of the swing. Assuming the tension force is non-zero at all points, draw the vectors to show the relative size of the tension force at the top and at the bottom. So I went over this in my vertical circles video. If you haven't seen that, you can check it out. But at the top of the swing, that is when we're going to have the least amount of tension. The reason for that, because at the top of the swing, the centripetal force is provided by the tension plus the weight force. And so because the weight force is helping supply the centripetal force, the tension force can be less. And so we can draw our tension as so. That's our tension right there. Now at the bottom of the circle, that is a different story entirely, because our centripetal force at the bottom, so this is at the top, and now at the bottom, the centripetal force is provided by the tension minus the weight force now. The reason why it's minus is because the centripetal force is provided by the net force that is pointing inwards to the circle. Now, as you can see, the gravitational force is pointing outwards, and that's the opposite direction to what we want, so that's why we minus. And so therefore, if we rearrange this equation, we can see that the tension force is equal to the centripetal force plus the weight force. And so in order for there to be a centripetal force, that tension force must overcome the weight force. At the bottom, the tension force is much, much larger. Now it's important to note that these are relative sizes, so the size that you draw doesn't necessarily matter, it just matters the relationship between them. So this must be greater than this. It doesn't matter if you draw it like exactly where I drew it. Now using the same scale, draw the centripetal force on diagram 2 at these two positions. So now we can use our equations that we did previously to help us. We can see at the top, the centripetal force is equal to the tension force plus the weight force. So it must be greater than the gravitational force plus the tension. And so we can draw those like that. So that's our FC right there. Now at the bottom, the centripetal force must be less than the tension force because we are minusing the weight force off it, remember? So that means we can draw it like so. FC. There we go. Show that the minimum speed of the ball must have during the circular motion is 3.43 meters per second at the top. Explain your answer. Okay, so again, I went over this concept in my circular motion video. At the top of the circle, as we explained up here, this is where our FC is equal to the tension force plus the weight force. And therefore, we can say that the minimum FC needed is when the entire centripetal force is provided by the weight force. And so tension is equal to 0. And so therefore, FC is equal to the weight force, and therefore mv squared over r is equal to mg. As we have masses on both sides, we can cancel those out, and therefore v squared over r is equal to g, and therefore with some rearranging, we can see that v squared is equal to gr, and therefore v is equal to square root gr. Now we know from previously in our diagram that the radius is equal to 1.2 meters, and so plugging that in, we can see that the square root of 9.81 times 1.20 is equal to 3.43 meters per second, and as you can see, that is the value that we're trying to find. The ball drops to its minimum speed of 4.43 meters per second at the top of the circle. Using conservation of energy, show that the angle at which the tangential speed of the ball is 4 meters per second. Using conservation of energy, show that the angle at which the tangential speed of the ball is 4 meters per second is theta is equal to 34.9 degrees. Okay, so this question may seem a bit daunting at first, but when you break things down, it starts to make some sense. So if we redraw this diagram just a lot bigger, we have our center point going like this, and we have our 1.2 meters, and this is our theta right here. The ball is going at 4 meters per second. Right, so, okay. So, as we know, the top of the circle is obviously the highest point, and therefore this point right here is going to be slightly below that. And so if we draw a little triangle, like so, we can see that there is a delta H right here. So that is a change in height between this height and this height at the top. And that's obviously going to result in a greater EP, right? This point has a lower EP than this point. What that also means is that this point right here has a greater EK than this point, because energy is conserved. And so we can figure out the EK at the top, we can also figure out the EK at this point, and we can see the difference, and the difference is therefore the difference in EP. And so we can do that right now. We can say that the EK at the top is equal to half mv squared, where our v in this case is the minimum speed, and that's equal to half times the mass, which is 0.25, times its velocity at the top, which is its minimum speed, is 3.43 squared. And that gives us a EK of 1.47 joules. Now we can get the EK of the current position, and that's again equal to half mv squared, where our mass is again 0.25, it doesn't change, and our velocity is our 4 meters per second, which is given. And so we can square that, and we get a EK of 2 joules. And so therefore the change in EK is equal to 2 minus 1.47, which gives us a change in EK of 0.53 joules. Now, as discussed previously, our change in EK is equal to our change in EP, right? Now, our change in EP is equal to mg delta H. Now we know our change in EP is equal to mg delta H because the delta H is the only thing that's changing. The height is the only thing that's changing. G obviously doesn't change, and the mass of the ball is not changing. And we can see in this scenario here that the height of the ball is the only thing that's changing. And so now we can rearrange for delta H, and we get our delta H is equal to our change in EP all over mg. And so therefore our delta H is equal to our change in EP, which we found out was 0.53, all over its mass, which is 0.250, times gravity, which is obviously 9.81, acceleration due to gravity, sorry. And that gives us a delta H of 0.216 meters. And so therefore now we know our delta H is 0.261 meters. And so if we look at the geometry of our triangle, we know that this total distance right here is just the radius, so that's 1.2. And so this distance right here is 1.2 minus delta H, and we can call this distance x. And so therefore x is equal to 1.2, which is the radius, minus our delta H, which we found out right here, 0.216, and that gives us x as 0.984 meters. There we go. Now if I just redraw this triangle down here, right? We know that this distance is 0.984. This distance right here is 1.2 meters. And obviously we're trying to find this angle. Now we have our hypotenuse and our adjacent side, so we know we have to use our cos relationship. And so therefore cos 0.984 all over 1.2 meters gives us a theta of 34.9 degrees. And as you can see, that is the angle that we're trying to find. Okay, question 3. Okay, so show that the period of a pendulum of length 1.2 meters that is oscillating in simple harmonic motion has a period of 2.20 seconds. Okay, so this is a very simple achieved question to start us off. We have our tension is equal to 2 pi square root length over acceleration due to gravity. And so we can just simply plug in our numbers. 2 pi square root the length, which is 1.2 meters, all over 9.81. And that gives us a period of 2.2 seconds. Explain what must be done to ensure that the motion of the ball approximates simple harmonic motion. So in order for the ball to approximate to simple harmonic motion, the angle at which it's released must be small. And so what I mean by the angle is if we have a ball right here, and this is the equilibrium position, this angle theta must be small. The reason for this is so that the motion can be approximated as a straight line, because small angle approximation, and therefore this allows the force to be proportional to the displacement. On the axes below, sketch a graph to show what happens to the ball's total energy over time until it stops swinging. Okay, so we have our energy on the y-axis and our time on the x-axis. So based on our intuition, we can imagine that if we release a ball and it's swinging, over time it's eventually going to stop due to frictional forces like air resistance. And so its total energy over time has to decrease, right? Because it eventually comes to a stop. If it never decreased, then it would just keep going forever and a day. So energy initially is max, and then it has a slow decay to nothing. It is possible to get the ball swinging by holding the top of the cord and gently shaking it back and forward. Explain how shaking the top of the cord can make the ball at the bottom of the cord oscillate in simple harmonic motion. In your answer, you should consider resonance and energy transfer. Okay, so this is a simple question of resonance. Resonance is when we add energy to a simple harmonic motion at its natural frequency. And so if we add energy at its natural frequency, then the energy will continuously build. A simple way to imagine this is if we have a child on a swing. This is a swing, and we have a child. Call me an artist. Right? The swing is swing backwards like this, and eventually it's going to swing downwards and through here, and back and forth like this. At what point is it best to push the child? We all know this. It's best to push the child on its way down, right? The child comes up and we push. The child comes up and we push. When you do that, you're adding energy at the pendulum's natural frequency. And so that's what resonance is, right? If you imagine the child is coming towards you and you push him as he's coming towards you, that's just going to stop the entire system because you didn't add energy at its natural frequency. And so therefore, applying that to this situation, the ball at the bottom of the cord will only start to shake if you shake the top at the pendulum's natural frequency. Therefore, you're adding energy into the system, and that's resonance. And because resonance is occurring, you're transferring energy into the system, therefore the amplitude will increase, making the ball visibly swing back and forth. Simple harmonic motion requires a restoring force that changes in proportion to the size of the displacement. Discuss what provides the restoring force when the ball is swinging in simple harmonic motion. Okay, so if we imagine the two forces that are acting on the ball, we have the ball right here in a free body diagram. We have the weight force coming directly downwards, and we also have a tension force. Now it's important to note that I have drawn the tension force at an angle in this scenario, but that would represent this position right here. If the position was over here, the tension force would act directly upwards. And so what that means is the tension force is changing direction. The only force that has a constant direction is the weight force. It's always acting downwards. However, the tension force is always pointing towards the center of the circle. And so if we imagine the ball at the extremes, so like right here, the tension force is going to be like this, and the weight force is going to be like this. We can draw a vector diagram from that. We can have our weight force coming down, and our tension force like so. As you can see here, there is a resultant coming off that, which as you can see, is at the tangent to the path that the ball takes. If I apply the force over here, you can see it's at a tangent to the path that the pendulum is taking. And so as I stated before, the tension force changes direction depending on where the pendulum is. This is when it's at its max displacement, this is when it's at this position, and this is when it's at this position right here. And so as you can see, as the pendulum gets to the extremes, the tension force increases. And so therefore, at the extreme, the tension force is the greatest, and therefore the resultant restoring force is also the greatest at the extremes. To emphasize this, we can draw the vector diagrams of this point right here. We can see that there is a weight force downwards, and that there is a tension force acting directly opposite to that. And you can see at this point, there is no restoring force. Similar thing over in this position right here, we can see that the tension force has not as great of an angle, and so therefore the resultant is not as extreme as in this case. And so yeah, that is all the theory that you need to know for this question to construct a answer. Sweet as. There we go.